In this final section of the chapter on matrices, we are actually doing something useful for computations for the first time. This section is called Gaussian Elimination in Systems of Linear Equations, and it will be a bit different from the previous chapters, although we will need some stuff from the previous chapters in this case. But we have a different focus, namely what a matrix is, before we study linear maps and so on, is just a big rectangle full of numbers. Numbers are made for computations, and there are certain computation that you can do with matrices, explicitly computations with numbers actually, that you can do with matrices for which we need the appropriate methods. And these methods I'm going to establish here. It's the Gaussian Elimination method, or Gaussian Algorithm is also another name for this method. You probably encountered this already in the physics courses, or maybe in, I think most of you should have seen this in high school, how to solve systems of linear equations. But here we will do this now mathematically rigorously. So we will argue why this works. We will do this in the language of matrices mostly, and then we will show why this algorithm can be used to determine solutions of systems of linear equations, for example. Okay, so again, let K be a field. I think I would have saved a bit of space if I had just written this on top of chapter 8, but anyway. So we're working over a fixed field. Now, the idea is we want to establish concrete solution methods for concrete problems. Namely, want to find methods for problems like the following ones. I will just give you some examples. The most important one, find the solution set of a system of linear equations. Of a linear system, which was another name for this. So really find the solutions for this. This is something where we can kind of write the coefficients of the linear equations simply in a big matrix and then use these matrices and do computations with them, as we shall see below. But this is kind of the most, many problems in the study of linear algebra are really then when you want to solve things explicitly, you have a linear system which you have to solve. It often boils down to this. So far we have seen several instances of this where we indirectly needed them. For example, when you want to show the linear independence of a set of vectors, it's basically a big equation in these coefficients where the coefficients of the vectors are then the variables, and we need to see if there's some solution which is non-zero, so where the coefficients are not all zero. Or, for example, when we computed recently the dual basis of an example of a basis, there we also kind of solved something with equations, and basically what we had there, although I didn't name it this way at that point, or I didn't notice that, we had a linear system. We had some coefficients in there. We needed to compute the coefficients of some transformation matrix and so on. So transformation matrices, for example, when you want to change bases, if you want to compute the coefficients of such a matrix or something, everything, in the end it all boils down to linear systems. So we really need also to really do some really interesting examples of this. Need a general method of finding solutions of linear systems. So far we've only seen in linear systems homogeneous linear equations have linear subspaces as solutions, and inhomogeneous linear equations have affine subspaces, so a linear subspace plus a particular solution. So this is all we know, but we want to do really compute them, really write down the numbers and have, if I write down a system of linear equations for you where I really have some numbers in there, either real or complex ones will it be, what is really the complete set of solutions of this system in terms, really given in numbers. Okay, so much for that. Now there is also some computations with matrices with which we will start in this section here that you can do. Namely, first of all, the most elementary thing maybe, compute the rank of a matrix. We have defined the rank, so which was the maximum number of linear independent columns, or the maximum number of the independent rows of a matrix, or the dimension of the image of the associated linear map. But of course this doesn't help in really computing unless the matrix is of a particular form, and we shall see this later. So compute the rank of a matrix, and we will really do a rigorous discussion of how we can really do this for every matrix. And similar idea, assume we have an invertible matrix, so quadratic matrix n by n. We have seen, so if it's invertible, there's an inverse matrix and so on, but so far we haven't computed the inverse matrix. So the idea is we want to compute a to the minus 1 in terms of, if I give you a matrix which which really has numbers in it, give me a to the minus 1, which also has numbers in it. So how can we achieve that? How can we get that? This is also what we will do in this section. Now, this time I'm dividing this section into 3 further parts, 3 subsections, which basically correspond to these 3 kinds of problems. And we will start with the middle one, which is kind of the easiest to discuss. And meanwhile, during these 3 subsections, we will eventually develop all the tools needed then for linear equations, systems of linear equations, which will be then the last subsection in this section. Okay, so subsection 841, computation of the rank of a matrix. Okay, and before we can do this computation, we will have to make some preparations. Now the idea is, if you have some matrix where you just can't really see the rank or something, the idea is to modify this matrix by some procedures and bring it into a nice form. And by nice form, we will see that this is later the so-called row-echelon form. This is a form where you can definitely see the rank immediately if you have a matrix given in this form. Now the idea is now I want to introduce some operations which I can perform to such a matrix, for which I can show that they do not change the rank. So if I have some of these operations which don't change the rank, I can perform them to bring something in row-echelon form. Then I can read up the rank by just performing these things and then reading the rank of the result, and we're done. This is what we will do in this subsection, and we will also see an example of this later, but first we have to develop this method. So these operations you can do to matrices. These ones I have to introduce first. Okay, so let m and n be natural numbers, and sorry for the cut, I made a tiny mess. Let A be an m by n matrix. And I want to give names to the row vectors of A. And to distinguish them from the way I wrote the column vectors, I can write them as A1R, A2R, to AMR, ordered like this, be the row vectors of A. Okay. We want to introduce 3 different types of operations which are performed on matrices and which are given in terms of these row vectors. So the first one, we take I and j between 1 and m, so 2 numbers of rows with I smaller than or equal to j. We define some operations Sij, which is a map from the set of all matrices S m times nk to m times nk. So it just converts a matrix to a matrix with the same size. And we define it in this way such that if A has these row vectors, Sij of A has the following row vectors. Almost the same, but we just change the order. Namely, we have an I and a j, and we just swap the ith and the jth one. So we kind of swap 2 rows. This is everything. So the first A minus 1 rows stay the same. Then the ith row is replaced by the jth row. Then we go on with the I plus first row and until the j minus first row. And then, so here we've replaced the ith row by the jth row, and here we replace the jth row by the ith row. So here it's AIR, and then we continue with AJ plus 1 R to AMR. So in words, S I comma j of A is obtained from A. By swapping the ith row and the jth row. Okay, so we just switch the order, and since if you think about the rank, so if I have the rank is now the dimension of the linear subspace generated by these vectors. And of course, if I then take the linear subspace generated by these vectors, the order doesn't matter. This is for the linear subspace, the order is irrelevant. So if I switch the order of these, nothing will change because I just want the dimension of the set of these row vectors and forget about the order. So obviously, if I do such a row swap, the rank of the matrix won't change. This just stays the same, and here in this case, it's quite obvious. Okay, second operation. For some row index I between 1 and m, and some number lambda, which is in K, but which is non-zero, we define an operation m, which I have an upper index lambda and a lower index I, which also takes an m by n matrix and gives back an m by n matrix. Whoops. And what I do is just multiplying the ith row of the matrix by the factor of lambda. So, so that's this, colon. So m lambda I of A, when A has still these row vectors up there. This has row vectors A1R and so on to AI minus 1R. And now we replace AI by lambda times AI R. And the rest just remains unchanged. Okay, so i.e. we say that m lambda I of A is obtained from A by multiplying its ith row by lambda. Okay, this is also elementary. And now if you think about this, about the rank, we need the dimension of the space of all linear combinations of these vectors. If we now multiply this by a scalar, this doesn't change the set of linear combinations because we could just change all the coefficients of this vector here by some multiple of lambda. So the span of these vectors will be the same as the span of these vectors. So also for these operations, the rank remains unchanged. Now, the third type of operation that we want to do. So for I and j to row indices and lambda in K, let E lambda, so lambda is an upper index and lower index I and j. Becomes a bit messy to write this down in detail. This again takes an m by n matrices and an m by n matrix and gives back an m by n matrix. So how is this defined? E lambda I j of A, what are these row vectors? The idea is now that, so A1R we let the first I minus 1 rows unchanged, and now take the ith row, and to the ith row, we now take the lambda-fold multiple of the jth row and add it here. So instead of AIR, we have AIR plus lambda times AJR. And the rest of the rows stays the same, so we have AR I plus 1 to AM. So just for some number j that we've predetermined, we add this multiple of this row to the row AIR. So let's also verbalize this, i.e. Eij lambda of A is obtained from A by adding the lambda-fold multiple. I hope it's still readable. Adding the lambda-fold multiple of the jth row of A to its ith row. Okay. Here it's a bit trickier to see. So here we replace basically one base vector by some linear combination with some other base vector. And it turns out that, not base vector, it turns lambda for multiple some other vector of this generating set. And it turns out that if you do these, this kind of operation, the rank of the space generated by these rows is still the same as the rank generated by these rows. This is not entirely obvious. This is actually something you have to prove. But yeah, we will not discuss this here. So this is, yeah, I will mention this later in the theorem. So we have three types. We have swapping rows, multiplying rows, and adding multiples of rows to other rows. A map of one of these types, so on one of the types A, B, C, is called an elementary row operation. Elementary row operation. That's a very important term here, elementary row operation. Okay, so much for that. So we manipulate matrices in this particular way. And so in case this was a bit abstract and a bit confusing, let me give you one simple example before I erase. So let's study the matrix which looks as follows. I have to squeeze a bit, sorry about that. We take just a 3 by 3 real matrix, 1, 1, 0, 1, 0, 1, and 0, 1, 1, and take this. So this is a 3 by 3 matrix with values in R, for example. This could also be any field, but anyway. So assume we have this as a real matrix. Now I want to show what if we apply elementary row operations looks like, just to yeah, make this maybe a bit illuminating for those of you who are a bit lost. So S13 of A. S is for swapping, and S13 means we swap the first row with the third row. So this means we just swap this and this. So the result is just, so put this in the first row, so 0, 1, 1. The second row remains unchanged, and the first row is now put into the third row. So here it's 1, 1, 0. And this is the result. So just swapping. So multiplication, that's very simple. So assume we have M2 minus 3 of A. So this means we multiply the second row by the number given here, minus 3. This means, so we start with this matrix and we multiply the second row by minus 3. So the result is just 1, 1, 0. And now minus 3, 0, minus 3. And the rest is 0, 1, 1. Okay, so very simple. And now finally, still can figure this. Hopefully it works. I hope it's still recognizable. Let's do the following adding of rows and columns. So E2, 3, 2, A. Now we have to look, probably every one of you are looking here, okay, what does this now mean? What is now I and J? This means we take the two-fold multiples, or the double, of the second row and add it to the third row. Okay? So this means the first and the second row don't change. Even we make a mess with the second row here, but this is just adding this to the third row, but this means the second row stays unchanged. So the first two are just the original ones, 1, 1, 0, and 1, 0, 1. And now for the third row, we have to take twice the second row and add it. So twice this one is 2, 0, 2. Added to this becomes 2, 1, 3. So this is this type of elementary row operation. Okay, now, before we study properties of this, I need to erase, but then we will see kind of how elementary row operations are useful and as I've mentioned already, and we'll do this as a theorem, it's kind of preserving, they're preserving the rank of a matrix, and this is then useful for our strategy of, what I mentioned in the beginning, transform a matrix into a matrix of the same rank, which looks simpler, where we can see what the rank is. And this is what we will do next. Okay. I just noticed I forgot one particular piece of terminology that I wanted to have in definition 851. Sorry about that. So let me just add this to the definition then. So now we've seen elementary row operations, we've seen examples, and now if we have two matrices A and B of the same size, we say that B is obtained from A via elementary row operations. So this is something which is easier to verbalize than to really write down explicitly as a formula. If we can take A, apply a sequence of elementary row operations, and then get B in the end. So formally this means if there exists a finite number of row operations, so if there exists K in N and elementary row operations T1 to Tk such that B is given as performing all these elementary row operations to A. So T1 composed with T2, composed with T3, and so on to Tk of A. Okay. Just something I want to mention and not explicitly write down. These operations must not be unique. So in general, there are several ways there are always several ways of how to transform one matrix into the other by elementary row operations in case it's possible. So in general, we don't know if it's which matrices can be transformed to which ones. This will be then studied later, but this is just a definition. So we say this is obtained from A, and in this case, we also say that A and B are row equivalent. This, in some sense, already means alludes to something which is not clear here yet, namely if B can be obtained from A via elementary row operations, then A is also obtained from B via elementary row operations. This is something we will discuss later, but this is kind of so symmetric in that sense. Okay, so much just for terminology I wanted to introduce. Now, I just want to give the main result that I mentioned already about the rank, but I want to have this just once and for all fixed. This is theorem 853. So A and B are M by N matrices with values in the same field K. So we let A1 to AR to AM to AMR be the row vectors of A, and we let B1R to BMR be the row vectors of B. Now, if A and B are row equivalent, then, and this is what I argued for the three types of elementary row operations individually, they don't change the span of the row vectors. So in this case, if they're row equivalent, then the span of A1R to AMR is the same as the span of the B1R to BMR. Okay, just in case you're slightly confused, so just think span means linear subspace, and the vector space we are in, just to orient you, this is the space of 1 by n matrices. So in this vector space, that's where these rows are living in. So the span of these is the same as the span of this. And so just in particular, this means, since we've seen in theorem, corollary 850, don't write this down, but there we saw that the rank of a matrix is the kind of the dimension of the span of the columns, and so if the span is the same, this of course means the dimensions are the same. So rank A is equal to rank B. Okay, so this means that they really preserve the rank as I indicated in the beginning. I will not do the official or formal proof here. For the first two parts I already told you that it's quite simple, and I will do the full proof in the lecture notes. But this is quite elementary. It's not too difficult, but it's just a bit tedious, so I will keep this out of this lecture video. Okay, so now we've got that. So the idea is now, as I mentioned, we want to take a matrix and transform it into a matrix where we can kind of easily determine the rank. And so this was this row-echelon form that I indicated, and this I want to formally define. Namely, once you see what row-echelon, or once you understand what row-echelon form means, it's obvious that this kind of gives you an easy chance to determine the rank. So we say that a matrix A, where we call the entries Aij, an m by n matrix for any numbers m and n. We say that this matrix is in row-echelon form if the following holds. And this is now something which looks quite bureaucratic, and I will give you an example. I'll kind of draw the general scheme of a row-echelon matrix immediately after the properties. So first of all, there exists some number r between 1 and m, such that everything below row r consists just of zeros. If r is equal to m, of course there is nothing below, so this condition is empty. But this means if there is some r which is then in between, this means that, Aij is 0 for all I bigger than r and for all possible j. Okay, maybe let me already draw the scheme here. So A will be of the form, this will now take quite some space, I guess. So let's say here we have somewhere the row r, and so everything here will just consist of zeros. We'll need quite some space, I guess. Maybe I'll do this later, but from some point on, everything which is below this dashed line in such a big matrix is just 0. Now, what about the rest? For the rest, there is a particular rule. For all I between 1 and r, so all the lines which are not, all the rows which do not just contain zeros, there exists a number ji in between 1 and n, so some column index here, such that everything left of this element, first of all we want Ai, Ji is non-vanishing, so there's some non-vanishing element at index Ji. Everything left of this, so all elements to the left of this element are 0, so Aij is equal to 0 for all j smaller than ji. So this is the first non-vanishing number in this column if we take it from the left. And we want the following. The different indices here are behaving like this. j1 is smaller than j2, is smaller than, and so on, is smaller than jr. Okay, so what does this mean? Here it means, so in the first row, let's start, there we have an index j1, so assume we have some, assume the first entries are 0, then we have the first non-vanishing is A1J1, so double, no, triple indices, beautiful. So A1J, and this, so A1 and this is J1, so this element, and then something happens, I don't know. So, but this is just what we have here. Now in the second row, there it means we also have some J2 where there's the first non-vanishing element, but by this condition, this index must be bigger than J1. So this means it must be a column which is to the right of this one. So it means strictly below this one, we need 0. So in the second row, here must be a 0. And then, of course, we might have more zeros. And then at some point, we have A2, J2, and so on and so on. And for then we have an index, A3, J3, which was kind of the first non-vanishing element in the third row, which then has to be to the right of this one because of the strict inequalities. So we always have to go to the right and then find a new element. So to write down the general matrix, I think I'm using the fast forward mode again, namely now. Here we have it. This is the general form. I hope it's readable. I did this in the script. I did this in LaTeX, so in the lecture notes. I hope it's doable. So here we've got this kind of threshold where below everything is 0. And here we have several elements here. So here we start at some point, and here we have to go to the right and still we start at some point. And the next one we would have to go to the right and start at some point, and so on. And here finally we have some final index, which is to the right of all the ones before where we started, and there anything. So about these indices, which are kind of here in this top right corner, everything just to the right of these elements here, we don't know anything. They might be anything, it doesn't matter. But we know that all these elements here with which the row starts, so to say, these elements are non-zero. This is the assumption there. Yes, and this is the general row-echelon form. Now, these numbers, the first ones in each row, the numbers which would be A, I, J, I, where I lies between 1 and R, are called either pivots, P-I-V-O-T, pivots, or leading coefficients. Leading coefficients, this term is mostly used for polynomials. So I will mostly use the term pivots when I refer to these elements. Okay, this is the row-echelon form in a general way. Oh, there are some dots missing. Very important, okay. Yes, so I hope this gives you a way of understanding this. I would draw you an example now, but I already don't have space anymore, so let me erase and then I'll give you some examples. I have to apologize to all native speakers of English who are listening to this. I mispronounced one word so far. I wasn't sure anymore, so I looked this up in the break. It's not called echelon, this word is pronounced echelon. So it's a row-echelon form, not the row-echelon form, as I said earlier. So let us see some examples of matrices in row-echelon form. So the following matrices are in row-echelon form. Row-echelon form. If I'm writing them, are they in row-Mescher form? No, anyway. Okay. First example, very simple. 1, 2, 3, 0, 4, 5, 0, 0, 6. So here we've got, let me do some colored chalk. This is here the first column, the first column index of the first pivot is 1. Here we have 2, here we have 3. And the pivot elements are then 1, 4, and 6. Now, next one, slightly bigger. 1, 2, 3, 4, 0, 5. Oh no, I have it differently. Let's do it like this. 0, 0, 5, 6. 0, 0, 0, 7. Here now the first column index of the pivot is 1. Here we have 3, and here we have 4. So there's now no pivot in column 2, and the pivots are this, this, and this, 1, 5, 7. Okay, finally, yeah, even bigger matrix. This really takes a lot of space here. 0, 0, 1, 2, 3, 4, 5, 0, 0, 0, 0, 6, 7, 8, 0, 0, 0, 0, 0, 0, 9. Whoops, this is a bit close. Okay, so like this. And keep in mind for the row-echelon form, there can be arbitrarily many columns which are completely 0 here. So here we see we have 2 columns 0. This doesn't matter. This doesn't contradict the row-echelon form. So here we have as first, the pivots are then here obviously 1, 6, and 9. And so the column indices are then here. So the J1 would be 3. This is the third column. J2 would be 5. This is the fifth column. And J3 would be 7, which is the seventh column here. Okay, so these are in row-echelon form, and just one example of a matrix which is not. So let's do 1, 0, 3, 0, 3, 4, 5, 6, 0. this is not in row echelon form, because here we have these two. If we would forget about the third row, it would be. But here the first non-vanishing term is to the left of the first non-vanishing term in the row above, and this is prohibited in the row echelon form. So this is not in row echelon form. Okay, now concerning the idea was now that we wanted to find a form of matrices where the rank is easy to see. So let's consider the row echelon form. Now, if a matrix A, an m by n matrix, is in row echelon form, and R is the number as in the previous definition, so as in definition 854. This means R is the lowest non-vanishing row. Then the rank of A must be R. This follows from the properties of the pivots. I don't write this down. So if we take a look, for example, so the rank now means the maximal dimension of, the dimension of a linear subspace spanned by the rows of this. So for example, in this case, maybe that's to enjoy the fun even more, I enter another row full of zeros. So this is now a 7 by 4 matrix. But if we take a look, so the idea is now, what is the rank of the linear subspace spanned by the rows? Obviously, this row doesn't contribute anything to the span. This is just 0, and 0 is contained in any span anyway, so we can just disregard this one. If we take a look at these three ones, if there is a linear combination of these rows, such that if we add the combinations here, they are, we get 0. This means that here we can only combine the first entry of this first row. So this means lambda 1 times this row plus lambda 2 times this plus lambda 3 times this. These two are irrelevant, so here we would just get as an equation that needs to be satisfied that lambda 1 times 1 is equal to 0. This means lambda 1 is equal to 0, so this must be equal to 0, and then we can argue again with this entry. There we also would need that the linear combination of these two should be 0, but then the coefficient of this second row must be 0 since this contributes with 0 anyway. So by the same argument, the coefficient of this must be 0, and then this must be 0 eventually anyway, which means these three rows are linearly independent. So maybe just this one sentence, so properties of the pivots, so basically that they are non-vanishing and that they are so aligned as they are. Properties of pivots imply that the first R rows are linearly independent. And this then implies this equation. Okay, so this means if we have a matrix in row echelon form, we know the rank immediately. But so the idea is now to start with any arbitrary given matrix, and we want to determine this of an arbitrary matrix. And we have these elementary row operations. So the idea is now, can we take an arbitrary matrix and bring it into row echelon form by elementary row operations? And luckily, the answer is yes. And this is kind of quite elementary, and that's a very old result, actually. This was already known to Gauss. Probably he used a different language and not this abstract language of matrices and so on, but the idea behind this is quite, is really an old thing. I think Gauss mostly used this to really explicitly solve systems of linear equations, which we'll do later. So this theorem is called Gaussian elimination, or this procedure also, Gaussian elimination. Basically, actually the Gaussian part would be the proof of this. So let A be an arbitrary m by n matrix, where m and n are arbitrary numbers. Then there is a matrix B in row echelon form in what am I doing now? Sorry. Now I'm writing echelons, I pronounce it now ECH. I'm sorry about that. Echelon. form. Wait, have I not written this correctly? Let me look it up. Yes, sorry, it's pronounced echelon, but spelled E-C-H-E-L-O-N. Sorry about that. So there's a matrix in row echelon form such that B is obtained from A by elementary row operations. By elementary row operations. Okay, the proof of this is really nice because it's constructive, because you really take an arbitrary matrix and give an explicit method of how to bring it into row echelon form by these row operations. Now, let's prove this. And so this method of proof that we are using now is called the Gaussian algorithm. Sometimes this is also called Gaussian elimination, this method. So let me call this method Gaussian algorithm. I'm not sure, but you might also have encountered this already and did computations with it in your physics classes, but let's do this now really from scratch and mathematically with all details. Now, how do we start? So we have an arbitrary matrix given, which might be arbitrarily complicated. So first of all, we might assume we have some matrix given. So we might have some zeros somewhere here, or even the whole column might be zero anyway, but assume we have somewhere, we have some element, which I just label star, which is non-zero. So everything from here we have, so full of, here, arbitrary elements. So, but assume we have just some row below that the first ones have zero in the first coefficient, but in the first column, but some row has not. So to bring this into row echelon form, obviously kind of the first non-vanishing entry should be in the first row. So the first thing we need to do is to bring this to the first row, and there's particularly an elementary row operation which is perfect for doing so, namely just swapping two rows. So first of all, we search for the first non-trivial element in the first column and put it into the first row. Now, let's do this formally. Put J1 to be the minimum of all j in 1 to n, all column indices, such that there exists some I between 1 and m with aij non-zero. Okay, so this is the first non-trivial column. Now, given that, we have to put this into the right position. So let I be some row with aij1 non-zero. Then, we take A prime to be the matrix we obtain now from swapping. So A prime is, we denote these entries by aij prime now for this matrix. And this should be defined as the applying the swap of the first row and the ith row to A. Of course, if I is equal to 1, nothing's happening. This is just the identity, but this swaps in case it isn't. Okay, now A prime this is a matrix of the same rank, which has at least this nice property that the first pivot could be in the first row, and we have to create this now to be the first pivot. Now, what we need to do is to achieve, so now we have a matrix which can, looks like this. So we have here the first element somewhere in the first row, but now we might have also some entries. We could have anything here basically. So just some numbers, but we just know this is non-vanishing. And now to make this really a pivot element, the property that needs to have is that everything below here must be 0. So what we now do is that we kind of add the right multiple of this line to each of the line that's to follow, such that precisely this first element is cancelled. This means, so for each I, between 2 and m, so all the lines below this, we do the following. We put lambda I So we need the right coefficients such that if we add it to the number which is here, let's say for example, so this would be AI1 for some I. So here, sorry, AI1 prime, we have this as A1 prime, and this element here in the top left would be A11 prime. So to add a multiple of this to this and get 0, we must multiply this by lambda I, which is minus I1 prime divided by A11 prime. Since A11 prime now is non-zero, this is well defined. So, and now, so we add the lambda I fold multiple, so of the first row to the ith row. So this we do one after the other, so let me just write subsequently. Because if we do this to one line and then the next line, this doesn't change, so we can just do this in arbitrary order, what we want. Then it turns out, so if we do this, we call the result a double prime. And now to do once the formal definition with respect to these operations which add multiples of lines to other lines, this would be, so we first apply E21 lambda 2 to A. This would then mean, so cancelling the element in the row 2. Afterwards, we do E31 lambda 3 and apply this to the result of that, and so on and so on and so on. So here we would have ... until finally we have E lambda M1 and apply this to the result of everything that's in here. Okay, looks a bit messy, but I hope it's readable. So we can do this, and then we have basically cancelled everything in the first non-trivial column except for this first pivot element. So this means a double prime would then be of the following form. A double prime would be equal to, so in the first columns we might have zeros, we don't know. So then we have so the first pivot element, which would now be, let's say, B1J1 for some number B1, some non-vanishing number. But below this, we would have only zeros. Okay. Yes, like this. So below this, we will have zeros. And for the remaining coefficients, we just don't know anything. So here could be any numbers. Let's say B1J1 plus 1, and so on. Another fast forward, please. B2J1 plus 1 to B2N, and so on. And here we would have MJ1 plus 1, BMN. Yes, like this. So here we would have anything, but here we would have no, this is our first pivot element. So this here is kind of has nice properties. So basically everything that's left of here is fine, but we've got the rest. So what happens with these entries is totally irrelevant for us. So these we don't need to care about, but the interesting part is now this. So what we can now do is to forget everything around this, take just the matrix which has these coefficients. So let's say, yeah, let's call this A1. So this would be then B2J1 plus 1. Okay, that's a bit tedious. B2N, BMN, BMJN1 plus 1. Okay, now we need to come up with a solution for these. And to get this now, to make this element, or to have a pivot element here in this position, we just basically need to do the same thing as before, just restrict to this matrix and leave everything else as it is. So apply same method to this matrix A1. And this gives us a matrix which now has one more pivot. And now I have to erase and maybe draw this, and then we'll where we will be back in when I have drawn this matrix. Okay, here we have it. Now we had 2 iteration steps of this procedure, and we'll see that they can do this again and again and again. Now, we had achieved that this was the pivot element here, but for the rest we didn't know. So if we do the same procedure again, we will achieve a matrix which looks like this. We have here a second pivot element, somewhere here in the second row. So here's the first pivot, here's the second pivot. And we only know by this procedure that we have achieved something where this coefficient is non-zero, and below it's only zeros. Now for the remaining entries, so here and there, we still don't know anything, but we can now do the same thing again, namely by taking this remaining part. So these coefficients don't matter for row echelon, so up to here it's fine, but these have to be brought into row echelon form. And now we can take this submatrix and do the same thing again, and again, and again, and again, and again. And if you see where I'm going, so we just iterate and do it over and over. And we iterate this procedure, and after at most m steps, so it might be that we need the way or the end, but it might also turn out that at some point we don't have any columns left. So if you kind of reduce everything, there's only zeros left, so we can stop earlier. So after at most m steps, we obtain a matrix B in row echelon form. Echelon form. Okay, sorry, and the important part is form, and this is only obtained from the original matrix A just by applying elementary row operations. So swapping rows and then just adding multiples to others, so just this procedure over and over by elementary row operations. Okay, we will see an example in a second. Before, just a few remarks, or just one little remark and one overview. So, remark 858. Note that this matrix in row echelon form in theorem 857, this matrix B is not unique. So there are many matrices in row echelon form which can be obtained from a matrix by elementary row operations. For example, if we have one matrix, we can get more matrices in row echelon form obtained by elementary row operations. Namely, we just multiply some row of B by lambda. Of course, if we just multiply a row, if lambda is non-zero, this doesn't change anything about this row echelon property. So this is again in row echelon form. And of course, since it's just one more elementary row operation, we can obtain this from A. If we can obtain B from A, we can obtain this multiple of B from A. So it works, right? So this is, in general, not unique. Now, what we now want to do, and now this is what we have been meaning to do in the subsection all the time. We want to now combine the previous results to really get a method of how to determine the rank of a matrix. Namely, so we've seen the rank of a matrix in row echelon form is obvious, and we can bring everything into row echelon form by elementary row operations, and elementary operations, row operations don't change the rank. So we have a method. So these were the theorems that we need. So theorems 853 and 857. So 857 was this. 853 was that elementary row operations don't change ranks. So what we get from this is really that we now have a method of computing the rank of a matrix. Method 4, or grammar, to compute the rank of some arbitrary matrix, an m by n matrix with coefficient in k. So how can we now compute the rank? So first step, use use Gaussian elimination. to bring A into, to bring A is a bit rough, transform A into a matrix B in row-echelon form. By elementary row operations. Let me abbreviate like this, E-row. And so if we have done this, then the rank of A is the number of non-trivial rows of B. So it's just the number of rows which are not just containing zeros. Of B. And this is now something we can just always do. This is just like a machine, you can do this. I mean, this is something you can feed in a computer. Gaussian elimination, that's a fixed procedure. You could program a computer to do this. I mean, there are lots of computer algebra systems which do precisely this, where you can just tell your computer, okay, use this method again and again and again, and then spit out the matrix here and then count the number of non-trivial matrices. So this is something that a computer can do. And of course, now you might ask, okay, if my computer can do this, why do I have to learn this? The idea is that you should not just use computers, but understand them and understand how these computations work, since you should know what devices are doing actually when they do this. Okay, now, of course, this is time for an example. Okay, example 859. So consider the following matrix. A is a 4 by 5 matrix with real entries, namely the following one. A is given as, so 0, 0, 0, 0, 0, 0, minus 4, minus 3, minus 4, 2, 2, 3. 6, 3, 6 minus 3 I want here, 1, 1, and finally 0, 2, minus 1, 1, 0. Okay. If someone asks you now what's the rank of this, honest answer is no idea, because if you kind of take a look at these matrices closely, it's not obvious how many of them are linearly independent. So we take the span of these column vectors and need to decide how many of them are linearly independent. No idea. It's not obvious in this setting, right? So there are some matrices where you can kind of see basically some are linearly dependent or not, but here it's not the case. Now, what do? We want to now apply the Gaussian algorithm, and the first thing we see is, so the first condition was that in the first row we wanted to have this first pivot element. So the first non-vanishing column should have a non-vanishing entry in the first row, which is not the case in this setting. So here we have the first non-vanishing entry in column 4, but in general here there are non-vanishing entries in column 2. So what we need to do is now to make a swap of rows. And here we will just take, because this one later turned out to be, I mean, you've got some choice here, of course. You could now swap any of them, but we will now swap this one, because this turns out to be more this allows for neat computations, because kind of we have add multiples to these rows, and it's better to add multiples of 2 to 4 or 6 than other way around. So we this nice cleaner computations, but every possibility here you could do it. So it's just decide. So there's not the computation, but there are several versions of a computation which leads to the same result in the end. Okay, so we apply the swap S14. We swap the first and the fourth row. So our new matrix is O2 minus 1, 1, 0. So 2 and 3 remain as they were. 0, minus 4, 2, 2, 3. 0, 6, minus 3, 1, 1. And the final row, so we now swap places. So we have 0, 0, 0, minus 4, minus 3. Okay, so to make this number 2 here upstairs a pivot element, we have to kill everything that's below in there. So all non-zero terms, we have to add multiples of this row to this and to this to make to make these two guys vanish. So we start with the second row. So the first thing we do is we have to add a multiple of this to get 0 here. And of course we need to take twice this row to get a 4 here and to add this up to 0 there. So this means we have to add the operation, I call it E2, so multiple by 2, and now we have to take the second row and add twice the first row, which would then be E2, 1 with upper index 2. Now, this means so twice this added to this means, so the first line of course remains, the first row remains as it was. So here now we add twice this, so 2 times 2 is 4, and minus 4 is 0, hooray. Now we have 2 times minus 1, which is minus 2, which gives plus 2 gives us 0 here as well. So twice this plus this gives 4. And finally there nothing changes, so here it's 3. And the other lines are just 0, 6, minus 3, 1, 1, and 0, 0, 0, minus 4, minus 3. Okay, now this needs to go. So for this we need to add, we need to take minus 3 times the first row and add it to this row. So this would be the operation E minus 3, and now add the first row to the third row. This operation, E3, 1, minus 3. So we get 0, 2, minus 1, 1, 0, 0, 0, 0, 4, 3. So and now here we have minus 3 times this added to this. So in the first entry it's 0. Now minus 3 times this is plus 3, added to this is 0. Okay, now, okay, minus 3 times 1 plus 1 is minus 2. And finally here, so this doesn't change anything, so here we have 1 left, and the last row stays as it was, 0, 0, 0, minus 4, minus 3. Okay, now we see, so here's our pivot, that's fine. And now we see that quite some things have changed here. So we've already, this column is kind of, it's automatically 0, okay, so we don't need to care about this, and need to bring this into this pivot form. So we want to we want this to be the pivot of this in the second row. So that means we have to kill this and this. First of all, we see so if we can just start with the last row. The order doesn't matter. This is of course just minus this row. So we just have to add this row to this to get 0 downstairs. So we just need E1, 4, 2. Add 1 times the second row to the fourth row and get 0, 2, minus 1, 1, 0. Let's save some space here. 0, 2, minus 1, 1, 0. Okay, then 0, 0, 0, 4, 3. 0, 0, 0, minus 2 and 1. And 0, 0, 0, 0, 0. And now it's time to get rid of this one. For this we need to add 1/2 times this row to this. So E 1/2, 3, 2. And this becomes 0, 2, minus 1, 1, 0. 0, 0, 0, 4, 3. 0, 0, 0, and now 1/2 is 2, and so here we get 0, and here we get 3 over 2 plus 1, which gives 5 over 2, and 0, 0, 0, 0, 0. Now we see we have 3 pivot elements here, this one, and this one. We have 3 non-vanishing rows, and so this implies this matrix there has rank 3, and since we just applied elementary row operations, rank A is thus 3. Okay, it's really spacious to do this on the blackboard actually, not very efficient, but anyway. So this is how we can have obtained the rank of the matrix here. Okay, the next thing is the next subsection where we start to compute inverses of a matrix, but now since I want a fresh start, let me erase at this point and then start with the next part.